in the previous class, we have gone through the IPv4. What is the header format for IPv4? We have seen. Next, we will see is IPv6. So like we will be looking at like what is the header format for IPv6, and we will also see like why this IPv6 is basically required. What is the limitation to IPv4 that we were switching to IPv6, that we will also see. So this IPv4 is well designed data communication that evolved since the inception of IPv4 in 1970s. So IPv4 is also nowadays used, and that was basically implemented in 1970s. So it is it was very good in terms of accommodating uh, the users and also like transmitting the data or the packets from one user to another user or one station to another station. So, but because of some limitation to IPv4, there is a requirement to switch to IPv6. So IPv4 has some deficiencies or some limitations that make IPv4 unsuitable for the fast growing internet. So nowadays we know like there is a term like IoT. So most of the things that most of the devices that are being used nowadays are being connected to internet. So that means once it is connected to internet, they are being provided with an IP address. So as the large number of devices are being connected to internet, there is a large number of addresses are required in terms of addressing that particular devices. But in IPv4, so we have seen in IPv4 basically there are total 32 bits were used for addressing. So we were having 2 to the power 32 addresses possible in IPv4. But in IPv6, basically it is going to use 128-bit addressing. So it will be having possible addresses that is 2 to the power 128. So that is very large number if we compare even with the 2 to the power 32. Even the 2 to the power 32 is also a very large number. But 2 to the power 128 is going to have very high users, number of users that can be connected to internet. So that's why we are going to switch from IPv4 to IPv6. And also there are some other limitations we will just see here. So the first one is address depletion is still a long-term problem. So in case of IPv4, address depletion is one of the issue. That's why we are switching to IPv6. Another is like internet must accommodate real-time audio and video transmission that requires minimum delay strategies and reservation of resources. So in case of IPv4, the accommodation for like real-time audio and video transmission were not there. So, and nowadays audio and video transmission is most frequently being done. So IPv6 supports the real-time audio and video transmission. So that's why it is going to be one of the advantageous in terms of IPv6, and it was not, this functionality was not there into IPv4. That's why there is a requirement to switch. And also the internet must accommodate encryption and authentication. So in case of IPv4, there was no encryption and authentication system in terms of IPv4 for the data. So therefore IPv6 is required. So in this IPv6, there is a property of encryption and authentication also. So it basically provides some extra layer of security. So for security purpose, IPv6 will be more efficient. So in case of IPv4, there was no encryption and authentication provided. So these are the limitations of the IPv4. So to overcome these deficiencies or limitations of IPv4, basically the IPv6 was proposed and is now a standard that is used for internet protocol. So we will be looking like what is the IPv6 datagram format, basically the header format. So similar to the IPv4. So in IPv4, basically we were having a header and then the data. Data in the terms of like here it is saying like data or payload, we can call it. So in case of IPv6, basically there will be a header. Along with header, there will be a payload. So this is the payload and this is the header. So the header in case of IPv6 are basically called like base header. So it is base header. So it is named like this is the base header that is fixed of 40 byte. That will be a fixed size header that will be called the base header is of 40 byte. But in case of the IPv6, IPv4, basically the header was having a variable length between 20 to 60 bytes. But in this case of IPv6, the base header is fixed, that is of 40 byte. And next is the next portion is called the payload. So that payload is having the range between like 0 to 65,535 bytes. So it's like 2 to the power 16. So that means this is going to accommodate 2 to the power 16 bytes of data basically. So IPv6 header will be having 40 byte for the base header and 65535 bytes for the payload. So in that payload, what it will be constituting? So this payload will be constituting some optional portion. So in case of like the IPv4, the base header itself was having the optional section. That's why it was having the minimum 22, maximum 60 byte. But in case of IPv6, the optional portion is not part of the base header. So base header is separate, and the optional headers are optional parts or fields of the IPv4 are separately mentioned into the payload section. So that we will be looking at once we will be going for the uh, complete explanation of these sections. Okay. So what is the disadvantage in terms of advantage if we call out? So what are the advantages of IPv6 basically? So here it is going to provide large address space because it is going to use 128-bit long IP address. So it is having large address space. It is having better header formats. So better header format in the sense here options are separated from the base header and inserted if needed. So here the options part, options and padding were there into the IPv4 that were part of the base header itself. But here the options are being separated from the base header. So it is providing a better header format. Next is new options. So here in case of IPv6, it is having some new options. So these are going to allow more additional functionalities. So there will be additional functionalities with the new options available for IPv6. Next advantage, allowance for extension. So here extension of protocols if required by new technologies. So here extension of protocols can be supported by this IPv6 basically. It supports resource allocation. So in case of IPv6, it is having a flow label field. So this flow label field is basically used for resource allocation, means basically for traffic uh, resource allocation related to the traffic and all that will be done by the flow label. So flow label is like if we are sending a packet. So if a packet is part of a message, so it will be providing a label to each of the packet. Once it is reaching to the destination, it will be able to identify like these packets are part of the same data. So the resource allocation, so it supports resource allocation basically. That is in the form of flow level. We will be looking at the later slides also. It also supports for more security. So in terms of the IPv6, it is going to support higher security. So that security will be done with respect to the encryption and authentication options that will be available for IPv6. So encryption and authentication will be part of an option. So whenever there is a requirement of encryption and authentication, that will be given into the header format. Otherwise, there is no requirement, then it will be removed. So that is the part of an optional uh, field into the IPv6 header. Okay, so this is the basic format for IPv6 packet. So here, the first one, as the previous one is having like version. So 4-bit is used for the version, and the next is like 4, and then 4-bit of from here. So total 8-bit is basically used for. So basically this figure is of previous version of this IPv4. So the new updated one is like the priority. So PRI, this is basically indicating the priority and traffic control. So priority and traffic control is basically utilizing 8-bit. Okay. And the flow label will be utilizing the 20 bits. So flow level is the field that will be utilizing the 20 bits. So 4 bits for the version. So in case of IPv6, the version is 6, so it is fixed. So 4 bits equivalent to 6 is 10110. So this will be fixed in case of version field. The priority, so priority is basically priority is also called like priority and traffic control. So here priority and traffic control is basically used for like, so priority will be given like when there is a congestion into the network. So the same like this priority is similar to the one that is available into the IPv4 itself. Like when there is a traffic or congestion into the network or the link, the packets will be given preference. So that preference will be given, and based on the preference itself, if there is a congestion, some lower preference or lower priority packets will be dropped, and the high priority packets will be passed, or that will be considered for sending the data through the channel or link. Okay, so that is the priority. And also this priority, and it is supporting the data like the traffic control basically. So traffic control basically indicates like if there is a congestion and if there is no congestion, then what will be the flow for the packets. That is basically the traffic control is given. So that is defined in terms of this 8-bit itself. Next is flow label, and then the payload length. The payload length similar to the one that is in IPv4. The difference here is like here also the source address is there and destination address. So source address, it is having separated by 4 like part, means one part will be of 32-bit. So total is it you can count it to total, it is 8, 8, 16, 8, 24, 24, 28, 32. So total is 32-bit. So from here to here is 32-bit, but the addresses, the IP addresses will be of 128-bit. That's why 32-bit, 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 4 levels are there, 4 sections are there. So total it will be having like 128-bit. 128-bit for source address and 128-bit for destination address. One is here hop limit. So hop limit, it again is of 8-bit. It is similar to the one that is in IPv4. We have seen like this is TTL, time to leave. So time to leave is same as like if a packet is being sent, it will be provided with the value 8-bit value that will be ranging between 0 to 255 basically. So in that value, once it is passing through a router, its value will be decreasing. So once the hope value is 0, that means the packet will be dropped. So that is basically used for avoiding the infinite looping of a particular packet. And yeah, so before that, there is a next header. So next header, so one is like there will be a main header. Okay, so this is the main header. Out of that, there will be a next header. So each header, IPv4, IPv6 header will be having a next header. So next header indicate like uh, it is having different functionalities. So the different functionalities will be like here. So next header is having different functionalities. So if fragmentation is required or not, encryption is required. So this next header will be of like 8-bit. So this 8-bit will be indicating like what will be the next header. If the next header is required, these values will be given likewise. If there is no header required, the value will be no option. Like it will be having 0. So 0 will be getting hope to hope normal option. If a particular suppose fragmentation is required, the next header value will be 44. So this is the basic idea in case of next header. And yes, so the last one is into this is like last one is basically called extension header basically. So that we will be later on seeing. So this is the basic format of the IPv6 format here, datagram. So each packet is composed of a mandatory base header followed by a payload. So that we have already seen. So there will be a base header and then will be followed by a payload. The payload consists of two parts. One is optional extension header and the data from the upper layer. So whatever is the data as well as the optional extension header that will be part of the header. Okay. The base header occupies 40 bytes, whereas the extension header and data from the upper layer contains up to 65535 bytes of information. So the data plus extension header will be part of 65535 and 40 bytes will be for the base header. Okay. So this is the modified or the latest header format for the IPv6. So 4-bit for the version, 8-bit for priority, or it is also called like traffic class. Flow level will be of 20-bit basically. Payload length will be of 16-bit. So 16-bit, it will be indicating like what is the payload length. So the basic format we have seen like there will be base header that is fixed 40 byte. But this is the payload. Payload is going to have extension header plus the data. So what is the size of this payload that will be indicated by the payload length, 16-bit information. So this is 16-bit means 2 to the power 16. It is going to say like this much amount of bytes of data is stored by the payload section. Next header we have seen next header, and hop limit is going to define a time, that is time to live basically for a particular packet, source address and destination address, and if there is some value into the next header, it will be indicating like what is the extension header here. Okay, so if there is no value, no extension header will be here. So if next header is defined, so in that next header there will be another next header that will be the extension header that will be defined. We will later on see saying it like what it is basically. So here the priority and traffic class, what it basically indicates. So this field indicates class or priority of IP6 packet, which is similar to the service field in IPv4. So in service field, we have seen in IPv4, like different services were there defined by service field. The same is like the priority and traffic class will be indicating what type of services will be provided, that will be given by this. Here the flow level. So flow level field is designed to provide special handling for a particular flow of data. Special handling for the particular flow of data. So how it is basically done is, so here the flow level is field is used by a source to label the packets belonging to the same flow. So if the packets are belonging to from the same flow, the source will be providing a label to the packets. So to distinguish the flow, an intermediate router can use the source address, destination address, and flow level of the packet. So if a packet is there, so a router will be identifying like what is its source address, what is its destination address, and what is its flow level value. So this 20-bit flow level value, based on these three informations, a router will be able to identify like this packet belongs to which flow. So these three informations will be needed at the router side to identify, to distinguish a bit flow basically, a packet basically. Okay. So for default router handling, the flow level field is set to 0. So flow level field is set to 0 for default uh, router handling. Okay. So in case of next header, so next header is defined by like it is defined by 8-bit. So 8-bit ranging between 0 to 256. So starting with 0 up to 256. So different functionalities are given to different values. So if fragmentation is there, so its value is 44. Means if we are putting 54 into it, this 8-bit information, that means this header will be having the means the packet is having this header. Along with that, it is going to see like it requires fragmentation. So fragmentation, if it is 44 is written into the next header, that is basically indicating the fragmentation. So this fragmentation is same as the fragmentation that we have seen into the IPv4. So here it is part of an optional one, but in case of IPv4, it was the mandatory one, like it was a part of the base header. So here, once some of the portions, some of the functions or the services are big part of the optional header, then it is going to reduce the complexity of the IPv6. So this is the advantage in case of IPv6. Okay. So here the next header indicates the type of extension header. Type of extension header if present immediately following the IPv6 header. So that means it indicates like after the base header, what is the next header. So like there will be a base header, then after base header, there will be a next header. So that will be like extension header. This is the base header. Then after the next will be the extension header. So if there is any extension header, that will be the available next to it, and this will be part of the base header. So you can consider here is, so this was the up to here. This is the fixed header that is of 40-bit. Sorry, 40 byte. So 40 byte base header that is fixed. So if the next header is having some data, like suppose it is having the data 44, that means instead of extension header, so this will be the 40 byte fixed. So but 40 byte it is fixed. If there is 44 here, so that means there is an extension header just after that. So along with this, there will be an extension header. This extension header will be decided by the next header value. This is here. In some cases, if it indicates the protocol contained within upper layer packets such as TCP and UDP. That means in some cases, it will be either providing some services, like what services is being mentioned further for that particular packet, or in some cases it indicates like what is the protocol contained by the upper layer. So if upper layer protocols are there, upper layer packets are there, so what these contains, what type of protocol this they contain, that will be indicated by this next header also. Yeah. So extension header, in order to rectify the limitations of IPv4 options field, extension headers are introduced in IPv6. So some of the limitations of options field were there. So to remove that, there is an extension header. So extension header is nothing but the option only, okay, but it is defined here. So it is not like it will be always available. So if in option field, whatever is the properties that is required, that only will be considered in extension header. That will be defined previously in next header portion. So that will be 8-bit data. With 8-bit data, it will be defining the data related to the extension header. So suppose into the extension header, some data will be there. So there also in extension header, there will be a next header. So if in extension header, some next header is also need to be added. Suppose they wants to add like 44, like fragmentation, and also they wants to have an encryption. So two extra headers will be used, extension 1 and extension 2. Okay, so extension 1. So in extension 1, the next header portion of extension 1 will be containing the next value, that is 50, for the encryption and security. So the extension header mechanism is a very important part of IPv6 architecture. The next header field of IPv6 fixed header points to the first extension header. So the next header of the fixed header point is going to indicate the first extension header, and this first extension header points to the second extension header, and so on. So the same way, like here, the next header value will be indicating the extension header, and into this extension header there will be a part that will be the next extension, that will be the next extension. So after this extension 1, what is the next extension will be mentioned into the next extension of extension header, basically. Okay, so there are different types of extension headers. So the one is like hop by hop options. Okay, then source routing, fragmentation, authentication, encryption, security payload, and destination option. So what is meaning? So hop by hop option, into the hop by hop option, its meaning is like whenever the source needs to pass information to all routers visited by the datagram, this option will be used. So it's like if a packet is there, okay, and if source want information, or source needs to pass a particular information to all the routers through which this packet is being transmitted. So there are different routers in between. So if the source is there, source want to pass some information to these routers, then it will be using hop by hop option. Okay, and here is also like a jumbo payload is there. So what is that meaning? So basically, in case of payload length, it is 16 bit is there. That means maximum to the power 16 byte it can send as a payload. But suppose the payload length is more than to the power 16 byte. In that case, this jumbo payload option is used. Okay, so that is jumbo payload option. Source routing. So in case of IPv4, we have seen the strict source route and loose source route into the IPv4. But these two parts are being combined together and put it into as a source routing. So source routing will be constituting the strict source route and loose source route, and that will be the part of an extension header. Similarly, the fragmentation. So fragmentation is the same as the one that will be used into IPv4. So the same is there. Okay, so this will be the extension header. Authentication. So it validates the message and sender and ensures the integrity of the data. So authentication is another extension header. If some authentication is required, then extension header value will be put for authentication. So for authentication, what is the value? That is 51. So 51 will be put into the next header. So now the packet will be authenticated before being sent to the destination. Encrypted security payload. So encrypted security payload is an extension that provides confidentiality and guards against okay. So whenever there is a encryption is required, so this ESP will be used basically. Okay. And next one is destination option. So here this destination option will be used when the source needs to pass the information to the destination only. That means there is no intermediate routers will be given the information. That information will be only provided to the destination only. In that case, the destination option will be used. Okay, so in intermediate routers will not be permitted to access that particular information, that is the destination option. Okay, so next is like what is the priority? So in priorities, we have seen priorities and traffic control, traffic class basically we have seen. So in priorities, so out of the 8 bits, so priorities are basically of 8 bit. So out of this 8 bits, only the 3 bits are basically used. So out of this 8 bit, only 3 bits are being used currently. Okay, so 3 bits are used. So with respect to 3 bits, only we will be having the option 0 to 7, or sometimes it is 3, or basically it is 4 bits basically used. So starting with like you can call it like these 4 bits are being used for priority. So 0 to 7 out of 4 bits that we are using means 0 to, it will be going up to 15. Okay, so here 0 to 7. So 0 to 7 is basically used for congestion control traffic. It is basically used for congestion and the value of this between like 8 to 15 is basically used for non-congestion control traffic. So if we are going to have the priorities, so priorities will be given like likewise. So it will be having the priority like if it is 0 means it is low priority, 7 means high priority. So we can go like this is high and this is low. So if it is 0 means no specific traffic is there, so that will be having a 0 priority. Okay. So if a source adapts itself to traffic slowdown, when there is a congestion, the traffic is referred to as congestion control traffic. So the traffic that is going to adapt with respect to the congestion available into the channel, that will be like congestion control traffic. Okay. So in congestion control traffic, it is understood that the packets may arrive delayed, lost, or out of order. So if there is a congestion, so it can be having a delayed receiving of the packet, or sometimes packet may be lost, or sometimes the packet will be arriving in out of order. So this is part of the like the congestion control traffic. Okay, so in congestion control traffic means there is a congestion, then how the packets will be controlled. So for that, this is the priority. So if it is 7 is the highest priority, if control traffic is there, interactive traffic, some attended bulk data traffic, unattended data traffic are there, background data is there, that will be having priority lower, and no specific traffic means there is that will be a lowest priority. So out of that, if there is a congestion taking place into the channel, the control traffic that will be having the control information will be given higher priority, and the one that is like background data is there, that will be given low priority. Some no specific priority is mentioned, that means that will be having the lowest priority. So that is the priority part. So next is non-congestion control traffic. So for that, it is having the range between 8 to 15. So 8 to 15, they are having different non-congestion control traffic. So in non-congestion control traffic, this refers to a traffic type of traffic that expects minimum delay. So if there is no congestion, it will be expecting the minimum delay. And also discarding of the packet is not desirable. So if there is no congestion, no need to discard the packet. Okay. And need retransmission is in most cases is impossible. So like if there is no congestion, so retransmission need not to be done. Okay. So in order to, in other words, basically the source does not adapt itself to the congestion. The source will not be adapting itself to the congestion if there is the traffic that is of non-congestion control type of traffic. So this is basically used for real-time audio and video data sending basically. Okay. So here some of the points are given for comparing the IPv4 and IPv6 packet header formats. So what this is, you can just go through it. Some highlights are just given. So here, so header length field is eliminated in IPv6 because the length of the header is fixed in this version. So this is the difference between the IPv4 and IPv6. Header length format field is not available into IPv6 because the header length is always fixed. That is 40 bytes. Service type field is eliminated in IPv6, and priority and flow control field together makes it to the service field basically. Total length field is eliminated in IPv6 and replaced by payload length. This is the difference. Yeah, the identification flag and offset fields are eliminated from the IPv6 header. They are included in fragmentation extension header basically. So likewise, the TTL field, that is time to leave, is called now the hop limit here in IPv6. So some of the points are given with respect to comparing IPv4 and IPv6. Next, comparison between IPv4 options and IPv6 extension headers. So what is the difference between options into IPv4 and IPv6 extension header? So here, the no operation and end of operation options in IPv4 are replaced by pad 1 and pad n. So in case of hop to hope options, we were having pad 1, pad n. Okay, and along with that, we were having the payload that like jumbo payload that is used when higher payload is being transmitted. Means the payload, if the payload is greater than to the power 16 byte, in that case we'll be using the jumbo payload options, while hope to hope options are available into the extension header. Pad 1 and pad n is basically going to indicate, yeah, the no operation and the end of options. Okay, so the record route option is not eliminated or not implemented in IPv6 because it is not used here. So there is no need to record the route. So that's why there is it is not used into IPv6. Timestamp option is not implemented because it is not used here. Not used. Also, the source route option is called the source route extension header in IPv6. So source route options and that is having the loose and fixed one that is being considered part of the extension header into IPv6 basically. Fragmentation field in the base header section of IPv4 have moved to fragmentation extension header in IPv6. Authentication extension header is new that is being added to IPv6, and also the encrypted security payload extension header is new to IPv6. So some new applications are being added into IPv6, and some previous one, some old one that were there into IPv4 were removed. That is not part of the IPv6 because it is not being used. So this is the basically a comparison between the header and the options and extension of the IPv4 and IPv6. So that is all about the IPv6 basically. So the next topic that we are going to discuss is unicast routing protocol. So here, routing table can be either static or dynamic. So before going to understand what is the unicast routing protocol or what different types of unicast routing protocols are there, we're just looking at some information. So here the routing tables can be either static or dynamic. So routing tables can be static and dynamic types. So what is the meaning of static? Static in the sense, static routing table is the one that will be having the manual entries. So manually its entries will be updated. But in case of dynamic routing table, its values will be updated automatically when there is a change somewhere in the internet. So if some information are available into the internet or some changes are there into the routes between different routers and source and destination, there will be again change in automatically updation of the routing tables basically of a particular router. Okay, so a routing protocol is a combination of rules and procedures that lets routers in the internet inform each others of the changes. So the routing protocols are going to be the one that is going to update are going to inform each of the routers about any possible changes that are available or any possible changes that taken place to any of the routers. Okay, so that if any router is having like what is the traffic, if there is any what is the delay while sending the data, that information will be updated to each of the routers available. So that is updated automatically if it is of dynamic type of routing table. If it is static type of routing table, it will be updated manually. So basically always the dynamic type of automatic updation of the routing tables are basically done. So yeah, so here before going for the routing protocols, we will just see like what is an autonomous type of systems and what is how it basically different from the one that will be uh, taking place while once we are going to have a communication between different autonomous type of systems. So autonomous type of systems means a system that will be having different routers and different stations connected to each other. Okay, and they are basically uh, controlled by a particular agency. So okay, so these are the autonomous systems are there. It will be having different routers, but these autonomous systems are connected with each other. So if these are connected with each other, it is basically called like this this is basically the routing between two different autonomous systems. It will be called like intra-domain routing. And inside the autonomous system, if the routing protocols are being used, so that will be called like sorry yeah, inter. So this is the basic idea of the interdomain and intradomain routing protocol. So yeah, so the basic routing protocols are the popular routing protocols that is basically available is like divided into two different types: intradomain and interdomain. So intradomain, that is going to tell like if two autonomous systems or two autonomous networks are there, you can consider here if autonomous system in the sense like complete internet is there. So this internet will be part of like this is the internet. This will be constituting different autonomous systems. These are autonomous systems. So these autonomous systems will be connected with each other. Okay. Likewise, so different autonomous systems are connected to each other. Inside these autonomous systems, there are different stations connected with different routers, and this consists of total internet. Okay. So the same thing here, the routing should be done into the autonomous system itself or between different autonomous systems. So if the routing is being done between different autonomous systems, that is basically called like intra-domain routing protocol. And if the routing is within a particular autonomous system, that will be like inter-domain routing protocol. So in intra-domain routing protocol, the basic one is like the distance vector routing protocol and the link state routing protocol. In case of inter-domain, the routing protocol is path vector routing protocol. So we will be basically focusing on distance vector and link state routing protocol that is available in our syllabus basically. So here the RIP, this distance routing protocol, a distance vector protocol is basically named as like RIP. So RIP is routing information protocol. So it is called like routing information protocol. Link state protocol is called like open shortest path first. Open shortest path first. It is also named as likewise. Okay. So we will be starting with the first one like distance vector protocol. So like we will be looking like what is the distance vector routing protocol. So okay. So here it is given like A, B, C, D, E. These are the different routers basically. So suppose A, B, C, D, E are the different routers. So if it is having these are the routers. So each router will be having a routing table. So into the routing table, suppose this is the A's router table. So A will be having a table. In that table, first column will be for 2. Means from A, we are going to which router. So from A, we are going to A. From A, we are going to B, C, D, like this. And once we are going from A to A or A to B, what is the cost? So here cost is in the form of cost between each routers is given. So this 2 is given in the sense from traveling from any traveling of any packet from A to C, we'll be taking 2 cost, 2 as a cost. So that can be considered as 2 as a delay, you can call it, or 2 is the amount, or you can say like the complexity. So whatever you can name it. So it is basically like if someone wants to travel from A to C, it's going to have 2 unit or 2 unit delay, or in terms of delay you can consider. So this is the weightage given between these two links. So A and C is being weighted at 2. This is having 5, means by traveling from traveling A to B, it's going to take 5 unit of delay, or 5 unit basically. So this is basically like the cost of traveling from A to B. So that is given by cost. So the routing table for each of the router will be having 2. Then 2 means from where it is going, the packet needs to be done to be sent to which router. Then what is the cost of sending this to this router? And then what is the next? Next is going to say like once we are sending the packet from A to B, then what is the next router? Okay, so that is basically the next section. So once we are going to see that, so this is the optimized one. Like these are the optimized stable routing table. So these are the stable routing tables of all the routers basically. So this is the one once everything is normalized. Okay, but these updation of these tables are done. How these are done? We will be looking at like how this updation is basically done. So once it is completed, the updation is completed, it is called like a stable routing table. So a stable routing table will be having the shortest path from A to A. So A to A will be having 0. So next is here we can call it next is A. So once we are going to A to A, next will be A. When we are going to from A to B, because it is A stable, A to B we want to go. So A to B, B is here. So minimum distance will be 5. So you can just think in that way. So if we want to go to B, how we can go it? By directly we can go by 5, or we can go by 6 and then 4. So 6 and 4, the 4 and 2 will be 6. So 6 is there. So minimum weightage or minimum cost will be 5 itself. So it is 5. So once we are going to B, it will be directly going to B. When we want to go to C, 2 is the minimum one. So C will be the next router. When we want to go to D, so from A to D we want to go. So we can go directly by 3. So D is the one. Suppose we want to go to E. We want to go to E. So from A to E we want to go. So there are 2 different routes. So we can go like A, then B, and then E. This is one of the route. And then another one is like we want to go, then it is like we can go by A, then we can C, and then E. So in both the cases, what is the weightage? So it is our cost 5 plus 3, that is 8. 8 in this case. And 4 and 2, that is 6 to C. So if we want to go to E, we can go by 2 different paths, and the minimum weightage is to C. So that's why it is C is written. Okay, and its cost is 6. So this is how the tables are basically updated. So this is the final after updation of each data or each cost. The final table values are likewise. But how these tables are basically updated, it's not like if all the routers are turned on, they will be directly getting these values. So to get this value, there are some steps. So that is basically we will be looking at like how these tables are basically updated. So in distance vector routing protocols, basically the routing tables. So distance vector routing tables will be given. So here this is the first step is initialization. So whenever we are going to have updation, so initialization will be done. So the first step, this step or this tables that are looking like a complete one. So this complete table will be available after every step. So to get this table, we need to follow some steps. So the first will be like initialization. We will be doing the initialization. The first initialization will be like uh, AS table, and each routers will be getting its initial tables. Okay. So how it will be getting, like suppose at at A, the table of A will be getting like it can get the data from its neighbors only. So it will be updating its table from its neighbor, whatever the neighbors. So neighbors to A is D, C, and B. So whenever A wants to go, if a particular wants to go from A to A, it will be getting zero cost, and finally it will be reaching to suppose A. Then from A to B wants to go, it is 5. Then it will be going to B. Then A to C, it will be 2, and it will be going to C. Then D, from A to D wants to go, it will be costing 3, and then it will be going to D. But A to E, if a packet wants to go from A to E, there is no direct path because it can only think of its neighbors. So E is not the neighbor of A. So it will be taking an infinite uh, cost because it is having no route to go here. So because this is the initialization step, so it is not having any route to go to E. So it will be having a cost of infinite, and it will be having no intermediate one. Okay. So this is the initialization. So similarly, suppose the initialization of B, we can do it. So if the B's table is like, so initialization will be like, so each one having A, B, C, D, E. So in first of all, in a network, suppose this is the network, it is having 5 routers. So each router will be having its routing table with 5 destinations. 5 routers are there, so 5 destinations will be there. So okay, so from B to A, so B to A, it is going to take the cost 5, it will be updated, and it is A. From B to B, it is going to be taking 0 cost, and it is going to be B. From B to C, it can directly go. So 4 will be the value, and it is going to C. From B to D, so B to D, there is no direct path because B can uh, think of only its neighbors, ask only or identify the routes or the cost only by the of the neighbors. So B is having A, C, and E as the neighbor. So D is not the neighbor, so it will be taking infinite cost to reach it. And E. So to reach E, it can get the 3 as the cost. So 3, and it will be reaching to the E. So likewise, the initialization of table will be we can obtain for each of the routers. So this is the first step. The next step is after the initial tables is prepared for each of the router, each of the router will be sharing its table with the neighbors. So sharing table with the neighbors. And this is like first step will be initialization, then it will be sharing table with the neighbors. So whatever is table, initial tables are there, they will be sharing. So suppose here, uh, yeah. So in distance vector routing, each node shares its routing table with its immediate neighbors periodically, and when there is a change. So this sharing will be done only to immediate neighbors. Okay, so it can share its table only to immediate neighbors. So if A is there, so A will be getting the routing tables of D, C, and B. So at A, 3 routing tables will be shared. Okay. So here is given like how the updation is done. Okay. So how is update? It is updated. So its updation is given is like the old table of the A is this one. Okay. So we have seen like 0, 5, 2, 3, infinity. 0, 5, 2, 3, infinity is the old table. Okay. And this is the table that is received from the C. So once C is going to share, it will be only sharing the cost value. So for simplicity, it is given like A, B, C, D, E is also there. So A, B, C, D is the order that is same for everyone. So it will be only sending or sharing this value, cost value. So cost value will be like an uh, array format. It will be sharing to the A. So once it is shared to A, okay. So once it is shared to A, how it is updated basically is like we can just see here. So suppose this was the initial one, and C has shared its table. So C's table is this one. So C will be sharing what? 2, 4, 0, infinity, and 4. This will be the data that will be shared by C. Okay. And now the A value. So how the table of A will be looking like new? A, B, C, D, E. This is 2, this is cost, and this is next. This was the data shared, okay, by C. So with the help of C's table, A will be updating itself, updating its table. Okay, so here, so A was there. So how it will be updating? So it will be updating like it wants to update. So its value will be like, suppose it is at A and wants to go at A itself. So it will be updated. It will be like A to C and C to A. So between A to C going, it is going to have 2 as the value, and C to A. So this is the data by C means C to A going is required 2. So 2 plus 2 is 4 is required. Okay. So if by the C table A is going to update, so from A to A, C's table is saying like it is going to cost 4, but already it is having the 0 value. So out of these two, which one is the minimum? 0 is the minimum, so 0 will be retained, and it will go to next value will be A. Okay. Next, from A to B. So A to B wants to update. Okay, so A to B is initial value is 5. Okay, now the C's value is available here also. So now it is going to see if A to C and then C to B, because A wants to go to B, but the weightage is 5. Now C's table is also available, so it will be looking for any path between A to C, then C to B. Okay, C is sharing its table means it is sharing like, can you reach a, can the A send a packet through C to get a minimum distance? So this is the basically basic idea to check it. So from A to B, then it will be going like A to C and then C to B. So if A to C it is going, for that 2 is the weightage or 2 is the cost, and C to B 4 is the cost. So total cost is 6. But previously A is having a lower cost, that is 5. So this will not be updated. It will be same as this one. Okay. Similarly for C. So for C also the same way it is calculated. So from A to C it is 2 itself. This is the minimum. From A to D, from C. So how it will be updated? So yeah. So from A to D it wants to go, but with the C. So what is the meaning is like from A to C and then C to D. So A to C is 2 plus C to D. C to D is infinite. So it will be infinite. So overall it will be infinite. So it is saying infinite, but it is having 3. So 3 is the minimum. So 3 will be here retained. Next is A to E. A to E, it wants to go. So A to E, for A to E, how it will be going to like see A to C and then C to E. So A to C, it is having 2 value, and C to E. C to E is 4 by the C is table. So this 4. So total is 6. So now A was having infinite, but now after C is table, it is getting like by 6 weightage or by 6 cost, A can go to E, or the packet from A can go to E by 6 weightage. So it will be updating it to 6, and to obtain this 6 value, through which router it is going, through C it is going. So the next router will be C. So from going from A to E, C is the next router. So this is how it is updated. So this value will be updated. So this will be updated means this is how the new table of E will be looking like. 05236. So 05236, and here C will be updated here with respect to C. So E will be obtained. So from A to E, C will be there. So how it is obtained is basically it is obtained like with respect to C, a new modified table of A is there, and then what is the old table, by comparing these two, the resultant final table is obtained. So this is the table that is obtained by comparing with C. Now this one is there. So now again this can be compared with the B's table. Okay, so B's table is this one. Okay, so 5, 0, 4, infinity, and 3. So likewise with respect to each one, so it's not like only C will be sending its table to A. B and D will also be sending. Similarly, at the C, it will be obtaining, getting the tables of A and B and E. So by obtaining each other's neighbor's table, each of the router will be updating its table. So this is like automatic updation. But after final updation, the result will be this one. This one that we have seen, this is the like stable one. So stable routing will be obtained after updating the table, or after sharing that it's stable by each of the router to other neighbors. So after sharing, the final table will be looking like this, that is there. So if suppose there is any modification into that, suppose this is the route that is damaged. If this route is damaged, then again each tables will be updated. Okay, so because suppose some route is there, so by going from, suppose this is 7, suppose this is 7, okay, and from going from B to A, it is taking suppose 7, and B to C, C to A is taking 4 plus 6. If this route is damaged, in that case 7 will be having higher weightage, so new updated route will be this one. So when there is any damage to the link, the routers basically update itself based on the available minimum distance. So by preparing the routing table, its meaning is like how the packets will be routed. That is basically given by the routing tables with the help of distance vector routing table. The next we will be looking at the next type into the next class.